That would help. Good evening and welcome everybody. This is Obi-Wan Pez for and Simplex Pachinko. We are going to be doing some more math stuff tonight. This is my differential equations book, which we are going to, at some point, start a differential equations class. So if anybody is interested, I'm gonna make an announcement finally over in Ben Center's Discord server. So if you have interest in essentially taking a differential equations class, but either you want to do this as refresher, like I did for a real analysis class, and I like to do with Penn Center's complex variables class, although I think I might just sit in the gallery for that one. Or if this is your first time doing differential equations, but you've already taken Calc, maybe Calc 2, we can help you out and try and understand some of the stuff before you maybe have to go and take it for real at like a university or community college. It will be structured essentially the same way as my differential equations class that I taught at a two-year community college, and everybody's going to be hopefully getting some basic knowledge about what differential equations is and start looking at some maybe slightly different ways to like do the education process for math education. Zach, I know, had experimented with just having a bunch of us kind of sitting around and discussing exactly what was going on, and that's kind of what I'm going for. We'll see how well it works. I also have a lot of like random asides, which are really good to put in, like math history, especially with differential equations, with the invention of calculus, with all this stuff. So we'll get into it, see how things go. For now, though, we're gonna come over here, pop over to Exceladra. Alright, reset the canvas from last time. Okay. So there's kind of like a number of different ways that we go about discussing what functions are. I think most of the time we usually get the kind of standard discussion that happens in all pre-calculus classes, where when we're talking about a particular function, oftentimes we get kind of the diagram. It's going to look something basically like this. And normally we have labeled stuff that looks like this. And a lot of the issues that I get are students don't quite know exactly what all of this actually means. They'll see it and say like, okay, well, it's a thing that has a bunch of inputs and a bunch of outputs, and oftentimes they'll memorize the definition that's given to them in terms of it is a relationship that maps, inputs to outputs, and then they have to clarify exactly what they mean or how many of each they go to. So we do want to discuss just a little bit, like, what does that really mean, or what does that, like, how can we assist in describing that? Let's see. So hoping to get a little bit more. Yeah, that's better. Pop that up here. That's good enough. Okay. Everything's an experiment, so see how well this is gonna work for us. Alright, now I don't have to worry about the location of my face versus the location of my writing area, so that's helpful. So if anybody wants to help out in terms of, like, what does it mean, what have I learned in previous classes and things like that, what are functions supposed to be, feel free to chime in. I'm going to give you a few tips on, like, stuff that I've learned over the years, ways that I've described it to students, ways they have described it to me, and ways in which we have decided to understand each other. Or not. Okay. So a function is going to be a relation. And that in and of itself kind of warrants its own little aside. It's just sort of like a list of or either a list of or a rule describing how two sets are related. It doesn't have to have any particular, relations themselves don't have to have any particular rules. You could just say, like, okay, well, we want the relationship between people's ages and people's heights. And relations, kind of very generally speaking, can work with data analysis and, like, large sets of data, because again, there doesn't have to be any particular rules in terms of what people's ages and people's heights kind of are. I did have, growing up, a diagram that was hanging in our pantry. My mother's a nurse, so let's see, like, this is something like, okay, technically it needs to be like a breakdown here-ish. We have over here height in inches, and here we have age in years. And very generally speaking, right, we've got our 0 down in the corner, and we've got about age 20 is going to be, again, very generally, give or take when people kind of reach their final height and are not going to be growing anymore. So we can say, like, after this point, nobody's going to grow any taller, probably. Okay, and so generally speaking, we have like a distribution which is going to do something more or less like this. Alright, this is going to be sort of like the mean curve, which is modeled after a logistic function. And we'll discuss like what kind of function that is, how do you describe it exactly, what kinds of equation, what kinds of equations do you use to get it, things like that. Oh, the rack. Hey, Red Tree, how's it going? All right, and then there's also two other curves that are attached to this usually, which show like more or less the standard distribution of how people how people's heights will track versus that mean. So like this will be, I don't know, 90th percentile. And this will be like 10th percentile. That's not actually true, but yeah, it's pretty close to 60 inches, so that's definitely not true. Maybe. Yeah, we're doing all right. Didn't have a whole lot going on today, so we did a our oldest did a choir thing in the morning, and since they were doing choir practice and it's like the last time they're going to meet this year, this also means that all of the kids in her grade are moving up into wherever they're going to go for middle school. So some of the kids at this school are staying there, and there is a like middle slash high school for girls, and then there is another place where there is a middle slash high school for boys, and then there's, I think that one actually mixes, so like they'll take anybody. And then there's like the public grammar school. So these kids are getting scattered to the winds in the next, couple months. So this was their last hurrah. And so I drove my spouse to work after. And then I was like, you know what? We got this other town nearby. And by nearby, I mean it was like 7 miles. And when I plugged it into my GPS, it said 40 minutes. And I was like, no. No, that's very incorrect. Turns out I had it set for biking, because I've been biking, but... And then on the way home it was 15 miles, and it was going to take... Or no, I think it was just even 10 miles, because it was like doing the diagonal. and it was allegedly going to take 90 minutes. I'm like, okay, something's definitely wrong. And I was about halfway home and I realized, right. The method of travel is actually a variable in this. um, yeah, no, grammar school's like the place where you would learn your reading, writing, and arithmetic. I don't know of the particulars in English society if grammar is supposed to refer to that. I know in the US it's just shorthand for like the place where you go to learn grammar. But that could very well be a function of my ignorance. Very good question. So hey, right? Speaking of mapping, um, so what we generally speaking see here is that if we were to pick a particular age, let's say, where is this going to fall? 16? Cool. If we were to pick 16 here as one of the ages that we are to look at the heights of people within this age group, what we're actually going to see here is a density function, which very generally is going to look something like this. So we call it a normal distribution because generally speaking, when you have something that is considered normal, like height, like weight, like I hesitate to use IQ, but that is a potential answer. Generally speaking, what you see is that there are a lot of people centered around this particular mean value, and then from there it falls off in both directions, that there are people that are above this particular value and people who are below this particular value. And the amount at each individual value is going to decrease as we start getting away from the mean. So really what we'd see is like this diagram could be more like this. If we think of that as like a 3D representation of coming out of the board here, we'd see that there's, you know, this mean value that is skewed a bit right here, and again that's going to be our mean of the population, and then it falls off in both directions. I have in this particular case skewed a lot more data to the lower side, or a lot more diverse data to the lower side. So this is skewed right, I believe. No. It's skewed left because that's where the tail is. It's been a while. Yeah, generally speaking. Yeah. There's some sort of feedback against things that are too far away from the normal. Whether that be an actual physical manifestation within the environment, like if you're just extremely short, you're not going to be able to, if you're a giraffe, get the good food up top, and so you're relegated to competing with smaller life forms for food. So that's going to net be a negative. As opposed to the giraffes who reach higher are able to collect food from the lower sections as well as the higher sections. So they have access to more food. There is also a pushback on the height of giraffes, which is just the stresses, the amount of architecture that's required to keep the neck upright and not just fall over. Because there are giraffes whose necks are just too big and their bodies can't support it throughout their development. Right, so this whole thing can be thought of as like one big giant like 3D representation where we have a whole bunch of people around that mean and then a whole lot less as we start moving away. So if you see this as like, I mean, you could like 3D print a model of this. It'd be really cool. We could get a 3D model of a normal distribution that starts with like a fairly dense packet of how large babies are when they're born. And then as time goes on, it spreads a little bit more. So people will be on the shorter side, 50, 60 inches, and then also be on the taller side, 70, 80 inches. And so there's all those people who would spread into a much larger area, as opposed to when babies are born, they're basically like, I don't even know what the low and high ends on this are, like between 16 and 24 inches. Like, my kids were around 20, 21, somewhere in that area. Hey everybody, how's it going? Thank you so much for coming on over, Zach, and everybody over at Eat of the Two Eye Pie. My name is Obi-Wan Pez. This is N Simplex Pachinko. Welcome to the Simplex. So my particular area of research was into this little bit of number theory, which had to do with binomial distributions, which led to doing a whole bunch of math, like in a notebook somewhere, and discussing with my dean, who at the time was trying to create the Journal for Research in Progress at our particular two-year college. And have a copy of it somewhere. I don't want to dox people, but you know. Really? Did I not put it here? That's ridiculous. Okay, anyway. Cool. So we worked on getting a whole bunch of students interested in doing math research, and then started reaching out to our colleagues across the campus to say, like, hey, would you be interested in like helping out this particular student in this particular field? And so we became kind of a point of contact for research in the broader two-year college. It was really cool. Loved it so much. Tonight we're going to be doing some discussions about functions and things like that, so if anybody has any interest in sort of the more basic, like pre-calculus, please let me know if you, for instance, don't really understand why something is the way it is, or what the definition is, or anything like that. I am happy to go through and discuss as much as I can. I have 15 years experience of teaching our Precalc 1 and 2 class, which was functions and trig. I was the person who taught that class the most ever, I found out, because as the coordinator for the course, I had to do a whole bunch of data analysis on who taught the course and when. And yeah, even like over the entire course of the college, I was the person who taught it the most. And that's semester classes. So basically, how many times did I do the shtick on each individual objective? There were other people who taught the functions class by itself, and other people who taught the trig class by itself more than I did throughout the history of our college, but within the 5 years that I was doing data analysis, I was the person who taught the combined as well as trig the most, and then the person who taught our combined class ever out of the entire history of that class. So I kind of I like that one. I brag a little bit. And if anybody has any other questions that you would like answered, I can always, take a little break and discuss whatever anybody else wants. For the most part, we do our Q&A type stuff in Penn Center's Discord server. So you can drop things in there, and we will see if anybody does have any questions. There is a maths forum and a maths chat, and I can check either of those. So if anybody has any interest, feel free. Okay, cool. And again, other than that, we'll just keep on talking about functions, relations, all that good stuff. So as we were discussing here, if you look at people's ages versus people's heights, or I guess heights versus ages, I never remember which way is which. Y versus X, right? We can make a graph of that, and it ends up being this cool graph, which has a logistic curve, right? Growth starts out fairly small. It then becomes exponential as kids reach into or towards or into their teens. And then when it reaches out toward like late teens into their 20s, it levels off almost like an exponential curve, but upside down. So it reaches like asymptotically up at the top. So a logistic curve has both of those behaviors, right? It starts as an exponential growth, and then it ends as exponential growth, but like flipped over. It's a really cool function, especially if you do any differential equations, which, by the way, if anyone is interested in taking a differential equations class, unfortunately we don't have any credit or anything like that, but to at least get through some of the material and talk about stuff and have deep conversations, we're going to be doing a differential equations class. I'm hoping to start in either a week or two, depending on when I get my crap together. And it is basically the same course that I taught in the 2-year college level. So I have taught it, I want to say like 6 semesters, something like that. And it is out of a free book, so you don't have to pay for anything at all. It is recommended that if you are interested, I will have a sign-up sheet. I just haven't done it because, yay. Yeah. I've been trying to figure out my calendar for like 2 months now. It's fine. Blanking. So it is recommended that you have calculus experience and probably Calc 2 that you've done somewhere. So if you have taken an official class, or I guess if you have done like an online class with a bunch of people, that would also probably work out. Okay, so we were talking about people's heights versus their ages, and how this makes a like the mean itself is on this logistic curve, which goes like this, and then the 90th and 10th percentiles have their own logistic curves, which have their own behaviors. Then if you look at any one particular age, just up and down like this, that itself can have a 3-dimensional representation of the density meaning like how many people are at these individual percentages of heights, or percentile heights. So are they at the mean? That's going to be the highest value at anywhere along the curve. And then as we go further and further along, I was saying just as everyone was coming in, this is going to spread out as it starts getting toward higher ages. The normal distribution is not going to be so tightly packed as when we were infants, because we all pretty much started at relatively close to the same size, and then we finish up in a much wider range. Okay, so this is a relation. It gets us kind of a rule of how two particular sets are related, i.e. people's ages and their heights, but it's not a function. So a function is giving us a distinct and unique, not always unique, but a distinct mapping where we have a relation in which each valid input has one and only one corresponding output. I will shorten this, generally speaking, and say to my students that each input has at most one output. So that's like any particular value that you want to throw into this function, it's going to at most get you one thing back out. So we see that in this particular f here. We have a whole bunch of inputs over on the left, and those are corresponding to each of these outputs on the right. There is also the possibility that you're going to pick something that's outside the input to throw into a particular function, and then it's just going to tell you, yeah, you can't do that. That doesn't go anywhere. If anybody has any questions, feel free to ask anytime you want. Right, okay. So the relation that we had down here with our people's ages and heights, if we were to draw a diagram for this, we have people's ages on the left was our input. That was our variable going across. And then our heights were vertical. And what we had were a whole bunch of ages obviously like all of the numbers, which basically go from 0 all the way out to, we said 20 was going to be more or less where people will continue to grow. So like 20-ish would be about when people finish up growing. We said, okay, if you have like somebody's age, it can map over here. But then also at somebody else at birth or at any particular age can go to this particular value over here, or this particular value over here, or this particular value over here. So we've got, in this case, somewhere where our ages and heights kind of have this like multi-value property, right? Not everybody who hits age 15 is going to be 60 inches, right? They're going to vary. and a whole bunch of different values. It depends on the person. So we're going to get this sort of multi-value diagram, which shows us that a single age can map to multiple different heights. So that's a bit of a problem in terms of functions, but it's great for a different kind of relation, where we're just looking at what are their ages, what are their heights. And really the best mapping for this, I think, is this thing. We get our statistical spread of people who are at the mean value or off from the mean value at whatever percentile it is. Big Boss and SNK. Are relations a broader term than functions, as in relations can be used to describe any function? Yes. Or at least I have never come across one that could not be considered that way. So usually you'll also see in the first place that the definition for function has the word relation in it. And, you know, as long as people have told you what relation really means, then you could probably agree or disagree on their particular definition of function based on that. It may very well be slightly different than what I've got, and that's fine. This is just my particular, like, you know, pet definition, essentially, that I give my students when I teach our functions class. And like this definition here is pretty awkward, so it's perfectly fine if you don't like it. So yeah, relation is going to be either a list of, a diagram of, right, or a rule describing how the two sets are related. In this case, this diagram is a rule. I obviously did not fill out the rest of the diagram, but yeah, whatever, it's fine. I think you all get the point. Right, so this particular relation can be called a one-to-many relation, and in this particular case, this doesn't tell us that this is, or this tells us this is not a function. Right, because any one input may have more than one output. Alright, so we come up here and we say, well, f is a function, and that particular function is this relation, which we draw a diagram, we come out with a rule for it in like equation form or what have you. Each valid input, so these are the ones that are inside the input set, has one and only one corresponding output. So the blue definition precludes any of this nonsense, where we have something that's outside the input set in the first place. We're going to say, okay, you can't use that number. You can't use that particular input. It's not valid. And then we say from each of these inputs, we have one and only one output in the output set. And again, the one that I give my students generally, if I'm just looking for a real short, condensed version, each input has at most one output, because you could think of all sorts of numbers, which might include this one out here, which are like potentially something that you could just throw into the function. Right? I can throw a negative into a square root. If I'm dealing with just specifically real numbers, I can. It's not going to come out with anything nice, right? Its output is null. So it says, no, you can't do that. Braylon, good evening. Am I familiar with Azure DevOps? Nope. No. When we start getting into discussing when we start discussing all sorts of like computer architecture and things like that, I really don't know anything. I know the math that can go behind a lot of the stuff. Authorization key. Okay, so like I know some about public key encryption and all sorts of stuff like that, but yeah, I don't really know anything about like specific authorization keys. Developer operations. Yeah. Sorry. So when we throw out a whole bunch of stuff with maybe. So it depends on what you're doing, Big Boss, because if you are using mathematical formulae in which to do something, you could, in theory, be looking at something that is a either a one-to-one or a many-to-one relation. In which case, if it is many-to-one or one-to-one, those are functions. And especially if you're using like mathematical operations within your particular function, whatever it might be, like, you know, colloquial programming function. If your inputs and your process are doing, again, one-to-one or many-to-one, then they are, mathematically speaking, functions. Exchange access token with auth. I really have no experience with it, Braylon. So, like, I mean, maybe I have experience with the thing itself, but I don't know the lingo. So yeah, if you're writing a piece of, like, you know, Python or C++, and you start saying you know, what kinds of things are your inputs? I don't even know what I want to do. You know what? I had a lot of problems with authorization keys not connecting specifically Outlook. There were a whole bunch of times where my Office version of Outlook would just be like, and we can't connect. And it wasn't that Outlook was down, because everybody else was sending and receiving messages just fine. And it wasn't that XYZ was going on, like the internet was fine. And it was just like, my password was fine. It wasn't updated recently, because that also happened. Every time I changed my password, Outlook would go down, and I'd go in and be like, all right, here's my new password. And it'd be like, nope. I don't know what to tell you. Let me restart my computer 50 times, and then on the 39th time, it just happens to work. Hashes are nice, so if you're trying to... In fact, let's kill two birds with one stone here. Alright, so you need to input your password, the date and time. And like the hash that you get out of this thing is some sort of function, mathematical function of the like ASCII value of the password or something like that, and the date and time. Right, so return, I guess, not end, but whatever, it's fine. So if you're trying to get a hash key out of a function, in this particular case, you're using some sort of mathematical thing to pass like the ASCII version of a password and the date and time, and then it comes out with this hashed version. So in this particular case, your hash inputs are going to be, you know, the ASCII of a password and the date and the time. If you end up getting like somebody who just happens to have the exact same password 1 2 3 4 5, because that'll pass, the date and the time at which they create those things are not going to be identical to each other. And then if you're on the back end of this, you have no way of being able to create or sorry, if you're a third party, if you are Eve because you are always listening, you have no way of being able to recreate the original password based on the hash, even based on like maybe some information about what their password, or well, you wouldn't know what their password is because you could just use their password. The date, the time it was created, and also like a couple of other pieces of information. You still wouldn't be able to come up with the original password because it has been run through a mathematical function which uses these things. So it gets all sorts of messed up. We did use Duo for all of it. Yeah, I was not super happy with Duo, but that was mostly because they were forcing us to use this thing, which like nobody really wanted to use. It's a really long document. Yes, that was the point, I guess. So in theory, you should call the Duo API instead of going to Microsoft Direct? Question mark. I don't know. What's data time? Again, I don't have any experience with any of the API stuff. I wasn't on the tech IT side. I was strictly teaching. Oh, date time. Not always, right? But date and time is a very convenient way to get something that is like just a pseudo-random input to help change the hash away from just the ASCII of your password. Like, change your password into a string of ASCII and, like, you know, do some weird thing to it, separate it out into individual numbers and, like, add them up or multiply them together to get a really big product or who knows what, right? There's all sorts of possibilities of things you could do. And if somebody from the outside knows what you're doing, if they start, like, keeping track of the dates and times that they are able to create like Puppet accounts, and then if they can somehow read the ASCII that's coming through, or not the ASCII, read the hash that's coming through, they might be able to reverse engineer something. But it's extremely unlikely if you're using a sufficiently complex function, like mathematical function. All right, big boss. So square would be a function, yep. Well, truly random A would be a relation mathematically. Yes, because if it was truly random, then you could keep inputting the exact same input over and over and over again and get multiple different outputs. If it is the, hey Superbrain, if it is the pseudo-random lookup generator that we have now, right, you can pass a couple of pieces of information into it and always manage to get the exact same things back. That's a function. That is a strict function. So one of the things that like the lookup tables will do is that they have, you know, random seeds where they start. And so sometimes they'll use, like the Enigma code back from World War II. It'll sometimes, like, use information that you've plugged into the calculator to then change the seed that would go into your random number generator. So it takes, like, the, you know, last 5 key inputs plus the date and the time multiplied by this other thing over here and uses that to try and say, I'm going to randomize the location I get on this seed. But if you end up, I know the TI calculators, for example, right, you can actually just plug in. You could say, I want 3 to be my random number. Right? Do 3 store to rand. Am I getting that? Not exactly. There we go. All right, 3 store to rand. And so when you hit enter, that's going to tell you exactly what it's going to do. It's going to store 3 into random. So you get the random number generator to not be so random anymore. Okay, and then if I go to, there we go. And then if I go to here and hit random, right, just to do, like, we'll do 5 there, right? Keep track of those numbers in your head. And then if I do, all right, let's do, 5 store to random. And then I do random again, right? I get completely different numbers. But then if I go back and hit 3 store to rand again, and then do rand. I go back to the original 5 numbers that we had. Right? Exactly 100% the exact same numbers. So that was one of the things that I did when I was like, hey, let's get some random numbers. I said, take anything you want, something that is sufficiently complicated, and then store that into random. And like all of you are going to be different. So do like your phone number, do your birth date, do your tax ID or whatever, whatever you feel like. Just plug that in, store that into random, and now all of you are starting at a different location on the table. So there's like, an extremely small chance that that particular seed might somehow be the same as somebody else's. It wasn't going to happen, but, I am not teaching math in the UK. So I am staying at home and fixing up the house and doing all of the things that are necessary. I probably pride myself the most on cooking, so I have my cast iron pans, well seasoned and everything. All right. We're going to need to go grab some more water and prepare ourselves for the next section. We could talk about more function type stuff. We could talk about trig, calculus, number theory, basically anything you all want in terms of mathematics. Sorry, Brandon. Don't know that much about computer science, so. Damn it. All right, well, ads just hit, so I'll see you back in 30 seconds. All right, we're back. I mean, yeah, it's meant to be a function. But that's the other thing, is that it kind of still is a function because you never actually cook the exact same thing twice. And, like, you think you're doing the exact same thing, but, like, the quality of the ingredients you have, the exact, like, the way the pepper grew this time versus the one you used last time could be completely different, and their water content could be different, and so one might be more prone to burning if it has less water. The absorption rate of all of the individual ingredients is completely different every single time that you do this. The humidity in your room, the exact amount of time that you spend doing something else while you're waiting for this to cook. It is technically a function because you never actually get the exact same thing input twice. Right? Your inputs are wildly complicated. And as much as we'd like to think it's a function, or it's a, like, nice function where you always do the same input and you always get the same output, It is a very highly complex set of partial differential equations. We're running off the heat equation. We're doing the diffusion equation. We're doing... So it's unfortunate in some ways that like we're always kind of assuming that this is going to work out nicely. Yeah. Cooking is, I mean, like anything else in life, it's really just being able to adapt to changes on the fly that makes you a good whatever. You know, you learn a set of rules, but at the same time, you've got to go with the Captain Barbossa line from Pirates of the Caribbean. It's more of a guideline, really. Okay, so... The way we're looking at all of our individual mathematical functions is to say that, okay, these inputs have at most one output, so you've got a bunch of different ways that we could do this. Right, one is to look at all of the individual like diagrams that we could draw to get from one thing to the other. Right, our set of inputs to our set of outputs. You can look at the diagram itself to see if this is in fact a function. In this particular case, we've got here a many-to-one relation, and this is perfectly fine in terms of, you know, whether or not this is a function. Right? All we really care about is look at the inputs, and are the inputs going to have only, at most, one connected thing on the other end. If it splits into multiple pieces, that's a problem. If they all come together, that's perfectly fine. Alright, Big Boss. Have a good sleep. I'll see you some other time. And we're going to be doing some gaming later on this week. We'll do some more math stuff at some point. Lately I've been kind of tired at night, so I've been mostly just not streaming. But usually Tuesdays and Fridays are my nights. I may end up doing Wednesdays as well, because I believe there's kind of a gap with our math teaching in terms of our larger community. And just so everybody, I know you got this at Zach's, but nonetheless, this is the list of our math chads. The main 7 people who are on our list, who have agreed to be on the list, etc., etc. So we have Dawn at Dawn Does Math, Zach at E to the 2i Pi, most of you came from over there. Penn Center is a Canadian math department chair, and also teaches, has actually taught his actual students on Twitch, which I think is bold. Ian Stuckey, Obi is myself, at NSimplex Pachinko, Dan at Danny Highway, and Dr. Gold at Actual Education. So we do various educational type stuff and try and make sure that people are either becoming more aware of mathematics being taught on Twitch, or trying to actually like teach people how to do math. And in my case, it's not just how to do math, but also like the why and how everything works. So I really like to deep dive into. I've done this a lot with my students as well. I really like to deep dive into how mathematics works, what the historical context is for any particular subject, and then try and make sure that we have the cultural connections as well to understand, like, hey, you know, it wasn't really actually the Europeans who discovered this thing. My favorite example is, of course, the thing that gives me my name, the 2-simplex pachinko, is a reference to the... You've probably heard of or seen the game Plinko on Price is Right in the United States, where there is a coin, I guess, which is then dropped through a series of pegs on a board, and then depending on what hole it goes into at the bottom, you get a certain amount of money. So they put like a $5,000 prize in the very, very center, and then the ones next to it are 0. And then the ones after that are like 1,000, 500, and so on and so forth outward. So the 2-simplex version of pachinko is the Plinko board. TM, Price is Right, CBS, all that good stuff. And right, so the context that most people know it from is Pascal's triangle. So the thank you. And Simplex Productions coming soon. I'm working with some lawyers. Solicitors. So the Pascal triangle is what most people know when they see this thing. But the thing is that, like, Blaise Pascal was not the first person to discover anything about this triangle, except how it connects with probability. So, realistically, right, he was using something which came from the Arab world, which was the connection between this thing and polynomials. So, I always mess this up. You'd think I'd know by now. Punks. No, okay. So Al-Khwarizmi was the first person to really come up with like a larger, like algebraic structure in order to figure out how what we now know as algebra is going to work on a larger scale. How to balance the sides, how to balance the equation. So that was really Al-Khwarizmi's contribution. The one that I'm trying to think of... Al-Kharaji. Yep, okay. I always get him mixed up with Al-Jayani, who is the one who did the treatise on spherical geometry. So, again, Blaise Pascal only really did work on probability theory. And saying, like, okay, well, if we want to throw a fair coin that, or sorry, unfair coin with a, let's say, 70-30 split. Right, then we end up with, I guess really the letters don't, they don't matter. And it's a very important thing, right? If you go and take a combinatorics class, or statistics, or probability, or anything like that, you're definitely going to use this. And so, like, if we do 4 flips, the distribution of each of the individual probabilities is going to then be 1 times 0.7 to the 4th times 0.3 to the 0. Right, and then we get a plus. All of this eventually adds up to 1 when we do it all out. But the important part is, like, which actual terms do you want to use out of all of this? So do you want to use them all, or you're just going to get 1? If you want to break it down into a subset and say, like, okay, how many times am I going to get, or what's the probability that I'm going to get at least 3 heads out of these 4 flips on this biased coin, 70-30, then we're going to see here, with 4 flips, we get this distribution, 1, 4, 6, 4, 1. This is going to be then one possible way to get 4 heads, no tails. There are 4 possible ways to get 3 heads and 1 tail. There are 6 possible ways of getting 2 heads and 2 tails. There are 4 different ways of getting 1 head and 3 tails. And there's only one possible way, one possible way of getting no heads and 4 tails. So again, all of this stuff will add up to 1, our total probability of all of these things potentially happening, right? And then you just say, okay, I only want the cases where, like I said, we have either 3 or 4 heads. So what is the probability that we flip 3 or 4 heads on a 70-30 unfair coin? Okay, well then I take these 2 terms and I add them up. Just those 2 terms. So here, 0.7 to the 4th, I know that right off the top of my head, right? It's 343 times 7 is going to be 21, 23, 2401. And let's say it's 0.2401 times 1 on either side of it. Plus, all right, this is going to be 4 times 343. It's going to be 12, 13, 30, no, 1332, wow. 1332 times 0.3. It's going to be 39.96. That's 0.3996. Add those two things up, that's going to be a 50, 63, 64. Yeah, 64% likely, give or take, 64% likelihood. Right, it's just short. Alright, so that's going to be 0.6397, yeah. So anyway, Blaise Pascal did some great stuff with this, but he doesn't deserve the credit for like figuring out the triangle or anything like that. Al-Karaji was the one who came up with the binomial expansion. And talking about how, like, if we were to take 3x plus 2y and raise it to the fourth power, then we'd end up with, hey, look at this, it's the same numbers as before, it's just slightly different. This is going to be 3x to the fourth, one way of just getting 3x 4 times, and no 2y's, plus 4 times 3x to the third times 2y to the first, plus 6, 3x squared, 2y squared, plus dot dot dot. And again, we do the same thing here. It's just slightly different. The context is slightly different. And again, here we get a slightly different approach to what it is that we're doing. But again, Al-Karaji doesn't deserve the credit for figuring out the triangle in the first place. Right, so we were looking at all these numbers out front here and how they were related to like this triangular shape. Specifically, this row right here is what's going to give us all of our coefficients. But the true credit here belongs all the way back with Liu Hui from China in about, I think it was 300 BCE or something like that, where he said, let's just start with a 1 and let's continue downward on this paper by saying that every time that we move down a row, we're going to add the 2 numbers that are above this particular number in order to get the next number. It's a little fraught, it's fine. If you do this with a set of hexagons, so I use hexagon tessellated paper as the, I don't have any, do I? No. As the way to do this. You can also do it with diamond tessellated paper like this. But reason being, there are 2, as long as the point is down, you have 2 cells which are going to connect down into one cell. So if we go through here, you can say like this, we add the 1 and the 1 to get the 2 in the middle. So this is the contribution of Liu Hui, who discovers, okay, well, to get these ones here, we've got the 1 at the top, and then we also have a 0 next to it, right? We're not adding anything. He didn't actually say a 0 because his society also did not have 0 at this point. There was no such number. It was just that there's nothing there, so we don't add anything. Another interesting discussion in and of itself. Right, so again, along the side we still get 1s, and then here in the middle, this is the first time that we see a 2. And then we go down again. On the edges we get a 1, and in between we get a 1 and a 2 adding up to get 3 for both of these middle numbers. And then we get a 1 on both ends, and then the 3 and the 1 get us a 4, the 3 and the 1 get us a 4, and the 3 and 3 get us a 6. So Liu Hui was the one who really connected this to just the idea of doing any sort of number theory at all, in saying, like, let's just play this little puzzle. And realistically, and I think a lot of the other math streamers would also agree, this is really where the heart of mathematics lies. You know, figuring out how to do things is very nice, and it's very wonderful to have some sort of application that your mathematics will connect to. Believe me, I have a master's in applied and computational mathematics. It's great to have, like, a goal. But at the same time, right, the real heart of the subject is just, like, noticing a pattern and just playing with it. Yeah. This was also a problem. I kept getting... Oh, 1000s? Ah, crap. Well, that's fun. So Liu Hui did a bunch of really cool stuff on the technical, right, 9 chapters on the mathematical art. Figured out the Gogu theorem, which is the Pythagoras theorem, calculating heights of distances and objects that can't be measured directly. So, yep, you know, I kept getting them mixed up for some reason. So I think you're absolutely right, Maxi. So thank you. Yeah, Liu Hui was the applied mathematician. Yang Hui appears to be the theoretical mathematician. Rawr. Well, that is that's worth a save right there, so thank you very much. Right. And also thank you to Big Boss from way earlier. Curses. Woo! Jiaxian. Okay. I definitely need to look that one up. I also have Zhu's Pascal triangle diagram. Zhu Shijie, who Shijie. Okay. How much was you aware of Yang Hui's work? Click on the full biography. Yang Hui, born around 1238 in Shantung, now Hangzhou, in the Zhejiang province in China. Yeah, okay. Contain notes? Oh, okay. He obtained a fine edition of 9 chapters of mathematical art, which contains notes by Zhexian. On the edition, commented on by Liu Hui and later by Li Chunfeng. Notes by Zhexian have not survived, so we only know that Yang referenced them. Okay, so the biographies that I generally use come from St. Andrews University. They've got a particular... Where is it? They've got a particular database called... what is that? MacTutor. So the MacTutor database has like all of the biographies that I also pulled biographies from when we were doing Black History Month in February. We talked about the specifically Black American mathematicians who did not get the credit they deserved during their time, and the good news that we found, the silver lining, was that first of all, this database exists, and second of all, a lot of the stories that get passed down were guarded by a lot of the allies of allies of civil rights, and so we had a number of sources who would tell about, I believe it was David Blackburn, David Blackwell, yeah. It's like David Blackwell, oh, you know what? Yes, that's right. David Blackwell was given an invite to the Rosenwald postdoctoral fellow at the Institute for Advanced Studies in Princeton, and at the time, the president of Princeton was a raging racist and said, like, absolutely not, we're not going to hire him into that position. And like, his wife used multiple slightly less awful slurs, but still slurs, and said, like, we're not doing this. And the like many of the fellows at the Institute for Advanced Study were like, no, we're leaving. If you continue to do this and put off his appointment to the Institute for Advanced Study because he's black, we will walk. We will take the entire institute and move somewhere else. I'm sure Massachusetts is very, very nice this time of year. And the president of the university finally was like, all right, well, you know, you guys are doing a whole bunch of good work, I guess. And the, like, almost the entire Institute for Advanced Study, like the mathematicians, the physicists, the newly formed computer scientists in this thing were like, David Blackwell knows exactly what he is doing. He is a wonderful mathematician, and he needs to be on our team. So they, yeah. Yep, they absolutely flatten the opposition at the administration of Princeton. Yep. Yeah, that's pretty awesome. One of my, what is it? My mom's cousin went to Princeton and was I forget what her field was. It was like political relations or something like that. Which, interestingly, like another of my uncles from a completely different side of the family was in like foreign service and stuff like that. So it's pretty cool. Yeah. Anyway, she was at Princeton in 97 to 2000, give or take, that stretch, and then we went in 2001 to go visit her, and I was originally going to be a physics major, so I went to as a part of our personal tour that we had with her, we went to Einstein's classroom. So when he was at Princeton, we got to see, like, this is his room. That's his blackboard. Like, I mean, it's been cleaned and wiped and whatever thousands of times since then, but nonetheless, it was cool that, like, oh, he used to teach in this room. But I also didn't know, like, any of this history that went behind it either. That was something that I only found, this last year when I was really looking at trying to find stories of mathematicians of color, and specifically those of African descent. And so we were working on a project. It was me and two other people at my 2-year college, and they were like, "Well, send us your research on what you've found so far." And I was like, look, at this point I'm pretty much just like sending you a list of names and then starting to type out the stuff that's already in here. So, like, you should definitely just check it out yourself, because I also was not making the presentation because I had already left at that point. So but yeah, the highlight here is the standard practice was to have the fellows at the Institute become honorary faculty members at Princeton University, but this caused a problem because at the time Princeton University had never so much as had a black undergraduate student, much less a faculty member, and the administration was all up in arms. In the words of the president, the Institute for Advanced Study was abusing the hospitality of the university with such an appointment. And yeah, the Institute was like, no. We're gonna go elsewhere if you try to do this. Then Blackwell eventually got to University of California at Berkeley. So. Reading up on stories always like... Oh. Blackwell went to the University of Illinois and was interested in calculus. And then it wasn't until he took a course... Where is it? think that one's it. On Hardy's Pure Mathematics. So this is the book that like inspired him to become a math major. Man, it was on its 5th edition in 1928. Like, okay. And thank you everybody for following. If you are, really appreciate it. And we will hope to see you back at the Simplex anytime, whether for games or for math. Again, I'll try to stream on, I think, Tuesdays and Wednesdays for math, and then like any other time during the week, I'll just feel like, you know, whatever I'm in the mood for, it's going to be whatever I decide to do. So, all right, and we've got about 15 more minutes before ads are going to play, I think. So we'll let that get a bit closer before we actually trip the ads. Alright, let's move this over here. Thank you very much for the follow. Okay, so yeah, Young Hui, thank you very much. Who had taken some inspiration from prior individuals, had eventually come up with a number theory, like triangle shape, and then to come up with how it all works in terms of, again, number theory. Al-Karaji was then the first person to really get this into a binomial expansion, which worked off of Al-Khwarizmi's original work in algebra to say, or algebra, to get expressions and then eventually equations. And then eventually Pascal was able to come up with the probability theory application for all of this stuff. So that's my 2 cents on making sure we attempt at the very least to get proper attribution to the people who deserve it for each of their individual contributions, due to the fact that all of their contributions are going to be, you know, even people who work in the same area, right, are potentially going to be having either, you know, was it a parallel discovery, was it inspired one by the other, that sort of stuff. So we don't want another Newton and Leibniz going on. We've got enough problems there. Computer science, yeah. There was a lot of statisticians coming out of the historically black sectors, and I don't know if that was because that was like a growth area, or if they were like, here's just like a new thing, let's just go figure something else out that's not like, you know, all these old problems are going to be figured out already, or I just don't know. It's an interesting history, and there's some interesting patterns that we can look at as we start looking through history. Okay, so our inputs and outputs in this particular function, it passes the definition with this many to one. And again, this is something that I always tell my students is like, if your computer is broken such that you're tapping on your keyboard and it is doing literally nothing, or it's making a beep noise but not actually doing anything, like, that's a function. It's not a particularly useful function, but it's still a function. If you go in and change the keyboard such that these are now your rows rather than ASDFGHJKL semicolon apostrophe. Instead, you have AEOU, DHT, and S hyphen. This is still a function because each of those individual keys still only produce one particular thing. They produce maybe something you weren't expecting, but it doesn't matter. What matters is that there is only one output that is coming out from any particular button. So if I just tap the A key, I only get A's. If I tap the S key, I only get O's. Tap the D key, I only get E's. F key, I only get U's. G key, I only get I's. Right? And I can't technically guarantee that it won't do it like 1 in a million times. Like, you know, I'm tapping this and then like, oh, it went like that. Like, that's possible. I would probably think, given the nature of our keyboards and the reliability of our computers, I dare say that I would first blame user error before thinking that that was a genuine, like, genuine fault in the function or functionality. All right. So it's only when we actually see, like I was doing there, if it's all one letter and then just like randomly some other letter gets popped in, but I only hit the one button, that's a problem. So really it's a matter of like reliability. A function is going to be reliable if, as far as we can tell, it's only ever coming out with one particular output for any particular input. Now, holding Shift and pushing S is a different thing than just tapping S. It is actually a different input. It's a set of inputs, I guess, but right? And then the other option that we get sometimes is this. Right, we get our ins and outs like this, and this function, it is a function first of all, because all of our inputs only have at most one output that are corresponding to them, and then these are one-to-one. That also means that if you know what the output is, you should be able to backtrack and find out what the input was, what the unique input is. And we can talk about that in a bit, but so this is kind of like it's reversible, which we would call that invertible. And then we would want to look at like an inverse function. Oh, good. Yeah, I guess it could depend on the context. So if it's only injective, does that actually preclude the possibility of a many-to-one? Oh. Maybe I misread it. Is injective the other one? Which one's injective, which one's surjective? I never remember. If the outputs are the same, then the inputs must be the same. Okay. So surjective is a standard function, what we say here, which could be many-to-one or one-to-one. We don't know. Is that correct? Zach's going to be disappointed in me. All that time we spent in the real analysis class. Specifically onto, okay. Yeah, I think we might be getting into the weeds here. But yeah, that makes sense. Okay, so I think the idea is that if you are merely saying injective and that it's a function, I could be wrong, but doesn't that imply that it's also bijective? So it's almost like redundant. Or does that not necessarily have to be because the image and the image and the codomain don't exactly have to match? Yay! If both sets are finite and of the same cardinality. Okay. Surjective also implies bijective. Okay. All right. I'm going to step out for 3 and do my usual routine here. So I will see you in 3 minutes. We'll be right back. Thank you very much for sticking around. Hey everybody, thanks for sticking around. My name is Obi-Wan Pez, this is N Simplex Pachinko, you are in the Simplex. Simplex as a whole has to do with a bit of the research that I was talking about with Pascal's triangle. I then expanded this and said, I want to do this in 3 dimensions. And then I found some cool stuff, and I was like, that's really cool. And I commissioned, although I did not ever hand over money or collect, a 3-dimensional model of what would have been a little, 3-dimensional pachinko board, I guess. It was designed with a bunch of cylinders. I had originally wanted a hexagonal type thing that then the engineer who was in charge of this little project could like 3D print and make it all one piece. But he was like, nah, it's too hard. Let's do it this way. And he was just like, I'm just gonna take copper pipe and like stick it together. I'm like, I mean, you're the engineer, so so it was gonna be like $200 or something for materials, and it was gonna be about, I think, yay big, and drop ball bearings through the top, and it would go into all of its 3 possible directions that it could go at every level. Excuse me. And actually, it's the same as the picture that I have for my startup stuff here. So you can see over on the left, there's just a little really crappy drawing that I did to try and get across my point, like what it was that I was going for. Actually, I think my version of it was much worse, and this is one that a friend of mine did for me. He was like, oh yeah, here, you can have this as your like splash screen, and I was like, great, how much do I owe you? He's like, I spent like 10 minutes on this, like, and how much do I owe you for your time? And he's like, dude. Tonight is hashtag not sponsored by Dea Into the Haze IPA. All right, back to the math. Okay. So eventually we'll talk about inverse functions and other cool stuff like that. Consider the function complex to complex defined such that f of x is 2x. This is injective but not surjective. A equals 2b implies a equals b, but 3 is, oh, right. Okay, the number 3 is not going to work for integer. Integer is not complex. A. Yes, thank you. We're having a day. It's fine. Now, so in my complex book, it was always set up like this. So z equals a plus bi. So shortcut for z isn't solid, it's a complex number. But yes, it makes much more sense when you're saying it as you did, because that was set notation, not a random complex number. Okay, so when we talk about all this stuff, we got all of our relations, we got functions specifically, one-to-one definition here, and yes, as you had said, if we start with right, well, we don't need if we're doing a implication, but right, our one-to-one-ness of a particular function is going to say that if we have two outputs that are the same, they must have come from the same inputs. That's the only way that one-to-one functions can work. So that does not necessarily have to be true for our many-to-one functions, right? Y equals 1. Right? Perfectly valid, if boring, function. And then our one-to-one function could be something as simple as, you know, y equals 2x. Right, linear function is nicely one-to-one. Implied in this is, of course, our and statement that goes the other way. So we don't have to say it. That if two inputs are the same, then also their outputs are the same. Right, this is just the definition of function. So like we oftentimes will just leave this part out because, right, we know it's a function, we don't have to worry about it. Right, and again, it's unspoken because it's the definition of a function. Okay. More interesting. So something that is actually uniquely mine. I haven't seen pretty much anybody do stuff this way. I really heavily leaned in to the idea that we were going to do function transformations. And my students, in particular, have been working on this kind of stuff. Or rather, I worked on getting my students understanding with this for basically the last 10 years of me teaching. I came up with some of the pieces of this, some of the pieces were already there, but for whatever reason, I like basically took the entire functions class, you know, the first half of pre-calculus, and just said, all right, this is what we're doing. We're going to refocus all of our energy to try and get everybody to have function transformation as the basis for like a lot of the graphing and function stuff that we were talking about. So when we started out, we said, start out with something simple. We did all of the basic functions. So our linear, quadratic, cubic. You know what? Let's go the other way. We did the ones we did from the beginning. Linear, quadratic, cubic. We did square root, cube root, oh, absolute value. Was that it? It's been a while. Less than a year, but you know. That's differential equations. This is only slightly dangerous, it's fine. Just pull up something completely like, what are you doing? No, I don't have anything weird saved in here. This is all math stuff that I've saved. Okay. I'm glad I didn't reveal somebody's name. That's probably a good thing. Okay. This will be good enough. So yeah, our first day was kind of interesting. We went through, I discussed how mathematics is axiomatic. We went through mathematics as relationships and then historical connections. This historical connections thing took me like, I mean, it only took me literally one board or two, but I was really harping on this for a couple of years to try and be like, I was originally doing it as part of my honors seminar, but eventually our honors seminar collapsed, mostly due to COVID. And so I was like, well, I'm just going to inject it into my class because, like, everybody needs to know this. At least that, math history is a thing. You should not be thinking of, like... yeah, you should not be thinking of, like, the calendrical system as a permanent fixture upon humanity that existed for all time. It is not, right? Calendars started getting created because people were interested in finding patterns. Like, oh, when are we not going to have to chase our food anymore? Like... So yeah, I went through, is this, Alright, that's fine. I collected it anyway. I did some cuneiform on a piece of Play-Doh, so that was fun. My kids had triangular Crayola crayons, hashtag not sponsored, and they probably still have it somewhere, and Play-Doh. I think I've actually done it on stream before at one point. But you just like mash the Play-Doh into like a flat thing that'll fit in your palm of your hand, and then you take the crayon like this with the triangular point on your thumb, and you can actually press it in and make all the cuneiform characters that you need. Okay. Parent functions. Yeah, you got all sorts of really bad handwriting. Aha. Yeah, these are all the individual sounds that you can make in cuneiform. So I pulled up a few of them anyway. Square root function. Yeah. Piecewise continuity, domain range. Boo. Yeah. I don't want to get too much into it. Okay. So, yeah, you can see my use of the full diagram of our real numbers versus our... Oh. That was supposed to be complex numbers. That was us describing the Lagrange points and differential equations. I don't know why I did that. Applications of... applications of imaginary numbers. There we go. So yeah, when you're talking about imaginary numbers, we're using... I very briefly went through some little stuff on eigenvalues and eigenvectors, but like obviously I wasn't going to tell pre-calc students like, hey, here's something to look forward to. Most of them were like, I don't really understand. I'm like, that's fine, don't worry about it. Like, if you don't understand vectors, like that's pretty much the baseline that you need to understand it. So if you don't understand vectors, it's perfectly fine. But yeah, I went through and discussed, like, if we talk about this particular like how are eigenvalues used? So in this particular case with a -3 and a +5, that was saying like at whatever the vector is of this particular one, the 3 is going to be like a fairly strong force that's being felt inward along this particular vector, whatever that vector might be. I wasn't going to go anywhere. And then we got going the other way, a value of 5 going out, so it's going to be stronger, pushing out further, and then it forms like a direction field. And then I said, you know, when you get an eigenvalue that is an imaginary number, now you've got these circular, elliptical, whatever you want to have it as, in this case circular, direction fields, which always just keep it in a perfect circular orbit. And I said, oh, remember that whole JWST thing that's going on like right now that we were talking about? This was 2002, yeah, or 2022. Whoa. So remember that, JWST, we're out here at this particular Lagrange point, and it's not staying there. It's unstable. It has to go around it a bit, and it follows, more or less an elliptical orbit, and then it has to be corrected every so often. So I was being a little exaggerating here, but okay. So my big contribution to I was trying to figure out if we had anything else besides these 6, but whatever. Was that we have these parent functions. Right? That is what these are. And they have very basic rules which govern each of their particular XY properties. So generally speaking, we're going to do the whole, okay, let's just come up with a table of values for everything that we got here. So for y equals a linear function, it's just going to be y equals x. So it's an identity function. It's the exact same thing. For inputs and outputs, you just get the same stuff. No surprise there. All right, y equals, all right, it's quadratic, so now it's x squared. So we take whatever value we started with and square it. It's going to get us 9410149. Y equals x cubed is going to end up being negative 27, negative 8, negative 1, 0, 1, 8, 27. All right, now y equals square root of x. We're just going to do this last one. In this particular case, what are the convenient values that we can use? Well, we don't actually have a negative here. So like, right, we could just pad this out with all of our square numbers that we understand pretty well. So negative 1 has nothing that it's, you take its square root and you get in terms of real numbers. There was occasionally a student who's like, well, what about I? What about the imaginary numbers? And it's like, okay, well, where would you graph that? Given that we talk about graphing for all of these other ones, they're like, well, you can't. I'm like, all right. So then we'll hang on to this idea. And we'll come back to it. Algebraically, it might work, but again, graphically, it's not. Right, so you get parent functions. Something like that. Make the circle big enough, no one will ever know. So for this, with my students, I said, okay, these are going to be the baselines. These are our parent functions. These are the values that you get when you plug in our x's. You get these things out for our y's. The shift that I would like you all to make is that we are going to think of these as distances rather than as just numbers. So we're going to be going for the first three anyway, we're going to always be talking about these individual horizontal distances of moving one at a time. And then our vertical distances are going to be measured from our origin point. So what's an origin point? That's going to be the place that is at the origin for most of our functions. And in fact, the origin point was always just going to be the origin. It's just that it's not always on the function itself. So in the case of like 1 over x, for example, right? We get something that looks like this. Okay. The origin point is still at 0, 0. It's just that it's not a part of the function. It's not a value that we're going to get and we're going to plug in. So I usually have it be dotted like that. Makes it a little bit easier to remind myself that, and have students remind themselves, that this is not on the function itself, but it still is an important point. So in a lot of... There's a few different ways we could do this, right? So, and this is always the challenge whenever you're trying to teach in general. It's which way do you want to do it? Which way do you want people to start thinking about this? Eventually they're going to start thinking about it on their own and make it their own. But, like, where are you guiding things? So if I just do something like this, y equals x plus 2, right? And I want students to figure out what... That's all right. If I just want y equals x plus 2, right? What are the students going to do? Well, they're going to find all the individual values from their table of values. More likely, they're probably just going to figure out, okay, well, the y-intercept is when x is equal to 0. So this is going to be at 0, 2. Y is 2. It's going to pop up in there. And then we're just going to get something that looks like this. Et voila, we're done. Which, like, okay, sure. But again, how does that help you when we eventually go out to, you know, this one over here and say y is going to be equal to the square root of x plus 2? What does that do for us? What's going to be an easier way to think about it? And who's to say that that's actually what I was thinking either? We'll get to that in a minute. Alright, so the way that I did this was maybe a little bit different than what most people are thinking about. There are two ways to look at this. One is that we have here x plus 2 is equal to our y. Or the other way to look at this is that y is equal to x plus 2. So the context is slightly different. If I want y equals x plus 2, ... being just a vocal pause, versus y is equal to x plus 2, these are two different things. And in this particular case, you probably won't notice it or appreciate it. However, when we get out to this one, it really matters. Because if I say I want the square root of x plus 2, that's that. If I want y equals the square root of x plus 2, that's that. And again, those are two very different things if you don't already know that. I'm sure most of you do. You're still sticking around here in the middle of this session. So you came from Zach's. Chances are you already get it. Right? Square root of x plus 2, or square root of x plus 2. So in each of these cases, I do something slightly different. In the case of y equals x plus 2, what I'm going to recommend is that we're looking at it makes no sense in this particular case, but it's alright. It's fine. We're going to look at stepping this through. Alright, and again, it'll become a little more obvious why I'm doing this as we go through. To get from just having x to having x plus 2, I'm adding 2. And yes, I hear you say, what the crap, man? I hesitated on the identity function. That's how you know it's late. Yeah, that's how you know it's late. So we've got the identity function here, and then we take those secondary numbers that started with just having our x's copied all over again and add 2 to them to get x plus 2. Again, obvious, but nonetheless, this is to set up the awesomeness that is to come. So now negative 3 plus 2 is negative 1, negative 2 plus 2 is 0, negative 1 plus 2 is going to be 1, and 2, and 3, and 4, and 5. Respectively. There we go. I was thinking respectfully, and I'm like, no. That is not the word I'm looking for. Come on, Obi. Okay, whereas if I'm going to work at y equals x plus 2, I'm going to start with x plus 2 is my input, and the y values that we get out are going to be the outputs. In theory, we could have messed around with some... like I said, I'm a little tired. It's fine. Alright, take x plus 2 and y, and make those the same things that we had up top. So here, negative 3, negative 3, negative 2, negative 2, negative 1, negative 1, 0, 0, 1, 1, 2, 2, 3, 3. This is the parent function, right? That's all we care about. This is the parent function. Don't use that. Use the same color that I got up above. Otherwise, it's just not going to work. Okay? This is the parent function. But here's the thing. We've got x plus 2 now instead of having x. So in order to get from here to just having x by itself for this particular function, we need to subtract 2. So in order to subtract 2, this is going to get us a -5 for our x values with a -3 for our y's, a -4 for our x's, a -3, -2, -1, 0, and 1. Alright, now here's my x values, and here's my y values. If we do that on this diagram, right, we've got x is equal to -5, comma -3, -4, -2, -3, -1, -2, 0, -1, 1, 0, -2, and 1, 3. So those are the points we get for the orange stuff. Y equals x plus 2. Alright, where's our origin point? Our origin point, this formerly 0, 0, got moved to -2, comma 0. Which way did it move? Well, that looks an awful lot like it moved left 2 spaces. Somebody's alarm just went off down the street. Fun times. It looks an awful lot like this got moved left 2 spaces. And wouldn't you know it, where are those parentheses? They're around the argument. Whereas, if we go the other way, we look at this in terms of our... Again, this is like our y for the parent function. Why am I doing this? Do it in blue, because that's our parent function. Right? Y is just equal to x. So then take x, we need to add 2 to it. That gets us x plus 2. So now, right, these are the parent function values. And then we get our, let's do green. We get our x's here. And our final y values here. Where are those? This is -3, -1. That's that one. -2, 0. That's that one. -1, -1. Or sorry, -1, +1 is here. 0, 2 is here. And, right, 1, 2, or no, 1, 3, 2, 4, and 3, 5. And also, right, where is our origin point for this one? Well, it used to be at 0, 0. The y value got moved to 2. It looks an awful lot like we just moved up 2 spaces to get there. Right, it went from 0, 0 to 0, 2. And in the other case, at the extreme other side, we've got that it went from 0, 0 to -2, 0. So it went left 2 spaces. So now you can see that like the placement of these individual values is actually going to make a difference In this case, it doesn't actually make a difference to the shape of the graph itself, but it matters to which points it is pointing. And if at any time there is a function where just the placement of parentheses is not going to change, or like is actually going to change the values that we get out of this, then we need to look at this in terms of like, you know, both of these possibilities as being different things, right? Look at it in terms of the square root function. Right, we've got y equals root x plus 2. This is going to take us as here again. We're going to go with, again, x, y equals the square root of x just being the parent function. Parent function says, okay, we got 0, 0, 1, 1, 4, 2, 9, 3, 16, 4. And when we want not the square root of x, but the square root of x plus 2, right, this is telling us that we need to add 2 to these particular values. So, 0, 0 then becomes, we got a 2 here, 1 becomes 3, 2 becomes 4, 5, and 6. So again, parent function's in blue, transformed function has x values here and y values here. So how does that work up on the graph? All right, well, we got 0, 2. We've got 1, 3. We got 4, 4. Somewhere in there. I think I went a little bit overboard, but it's all right. Something like that. All right, this is going to be y equals root x plus 2. Cool. All right, what about the square root of x plus 2? Right, we still get the parent function, y equals the square root of x. However, here's the thing, right? Our internal parts of this particular function aren't x anymore. The stuff that we're putting into the parent function is represented by x plus 2. And the stuff we're getting out of the parent function is represented by the square root of x plus 2. So in blue, we still get our 0, 1, no, 0, 0, 1, 1, 4, 2, 9, 3, etc. Right? This is the parent function. But then, going the other way, again, we're trying to just get x by itself. So what do we have to do? Well, we got to subtract 2 from our x values to make that work. So then 0 becomes negative 2. 1 is going to become negative 1. 4 is going to become 2. 9 is going to become 7. Well, that's a little bit different. So then we go over here and we say, okay, These are our x values. These are our y values. So negative 2, 0. Negative 1, 1. Uh, 2, 2. And 7, 3. Somewhere out here-ish. Again, which one's which? Well, it's obvious. We know what's what here. Right? The origin point, the new origin point. It's going to be at 0, 2. That's here. And the new origin point here is going to be negative 2, 0. And again, this is consistent with what we saw with the linear function, wherein having the plus 2 on the interior portion of the square root meant that we end up with a function that moves left of its parent position, and then here when we have the plus 2 on the outside, the square root of x plus 2, that tells us that our new origin point is going to be at 0, 2. We're shifting up. All of these points, all of our distances are going to be increased in the y direction by 2. So that gets us 2 portions of like what addition means in function transformation. We've got here our f of x plus c with a plus d on the outside. So here c is a horizontal shift. It's a movement. It's by c, but it's in the opposite direction as what the sign is showing us in the first place. So oftentimes what we do is we say, okay, if it's in the opposite direction of this, we erase the plus and we make it minus. So again, opposite direction as whatever is actually shown here. And D, on the other hand, is going to be a vertical shift. By D. And in this case, this is going to be the same direction. That's when we take this and we look at the sign in between. So anytime you encounter a plus in pretty much any formula, it's going to represent this is the same as what's given. Anytime you encounter a minus in a formula that involves a like minus a variable, minus a constant, it's going to be like, oh, well, this is the opposite sign of whatever we're putting into it. Okay. All right. And yes, this looks a little tedious, maybe. But in order to understand like really where this is coming from, it really helps a lot if you end up understanding each of the individual steps as we go through. Reason being, right, if we have something that is y equals 5 times the cube root of 2 parentheses x minus 1 minus 2 on the outside, right? Draw this. How long is it going to take you? What tools do you need to use in order to get that? All right, let's discuss it in terms of function transformation that we have done. Now, I grant you, I have not explicitly laid this out what the other two multipliers are. But they are multipliers. And based on what we were just talking about before, you should be able, even without talking about it, right? What we want to do is start with the parent function and then go from there to find our x and our y. So create the x and the y based on the parent function. Parent function is going to be when we have the cube root of all the stuff on the inside. 2 parentheses x plus x minus 1. Right? When that shows up, we get our parent function, which again was going to be negative 27 is going to get plugged in, and it's going to output a negative 3. Negative 8 gets plugged in, and we get a negative 2 back. Negative 1 gets plugged in, we get negative 1. 0 is 0. 1 is 1. 8 is 2. 27 is 3. All right, these are the parent function values, and I should have done this all in blue because that would have made more sense. Right, what we're trying to do here is link up all these concepts, and I'm not being consistent. Okay, and then what's the stuff we're plugging into the inside, which then gets us the nice cube roots? Okay, that's going to be 2 times the quantity x minus 1. Okay, now look at the stuff that we have. If we want to get the y values to become more like what we see here for y equals up top, then what are the things we need to do? Well, we got this multiplier out here, we got this minus 2 right here. In what order can we do things to change, in order to get that? It would be easiest if we could first multiply by 5, right? That gets us a negative 15, negative 10, negative 5, 0, 5, 10, 15. It looks like 5 times the cube root of 2 parentheses x minus 1. And then how do we get that last bit? Well, we just need to subtract 2 from it. So 5 times the cube root of 2 times the quantity x minus 1, end your parentheses, end your root, and then minus 2 on the outside. So how do we get that? Okay, we'll just take the minus 15, subtract 2, you get negative 17. Negative 10 is negative 12, negative 5 is negative 7, 0 is negative 2, 5 is 3, 10 is 8, and 15 is 13. Okay. That's it. So this is y. All right, these are the transformed y values that we're going to put on the graph. Now, how do we go this way? Because what we want is the x values. Well, divide by 2 first. That leaves you with x minus 1. And then here, this is going to be a negative 27 halves. Negative 8 divided by 2 is going to be negative 4. Negative 1 half. 0, 1 half, 4. Oops. 27 over 2. Then, how do we go from there? Look, we need to add 1. So now this is all of our x values. So add 1 to negative 27 halves is going to be a negative 25 halves. Negative 4 plus 1 is going to be negative 3. Negative a half plus 1 is going to be positive a half. 0 plus 1 is 1. 3 halves plus 1 half plus 1 is going to be 3 halves. Just giving away answers, it's fine. 4 plus 1 is 5. And 27 over 2 plus 1 is going to be 29 over 2. Those are the x values. Those are the y values. And you know what, let's do 16. It's way easier to split in halves. Okay, that's going to be 8, that's going to be 12, that's going to be 4. It's going to be 2 way down there. Ah, those are x values. Oh, no. That's pretty much the same. So whatever, it's fine. Alright, so we get a negative 25 halves, 12 and a half on the negative side, and negative 17 for our y. So this is going to be 8, this is going to be 12, negative, and a half by negative 17. Way down at the bottom. And technically off screen. That's fine. We got it. Then negative 3, negative 12. So this is negative 4. All right, 1 half, negative 7. One, negative 2. I'm off a little bit, I think, but it's all right. 3 halves, 3. 5, 8. And 29 halves is going to be 14 and a half. This is 12, that's 14, and just a little bit more, matched with 13. So what does this look like? Well, this is going to be sort of that same S curve that we get from Q roots. It's just been stretched again in a particular direction. Okay, so all of our x values, what happened? Well, we shifted it 1 to the right. Again, if you look at the origin point, where was that? That was our 0, 0 here. So that's 1, negative 2 is the new origin point. When doing the parent functions, I also usually like to do initial values, so we can see like precisely where things are. The reason that I look at that is that all of our basic functions have the origin points at 0, 0, but they also have initial points, that's what I call them anyway, at 1, 1, and or negative 1, 1, negative 1, negative 1, like one of these other places. Not at 1, negative 1. That would be not a function. Right, so these initial points are always going through 1, 1. So that means that whatever this 1, 1 ends up getting translated to is really showing us what's happening to the function in terms of multiplicative distances. So, where'd it go? Oi, there we go. So, 1, 1, and negative 1, negative 1. End up going to 1/2, comma, negative 7, and 3/2, comma, 3. So those points are going to be now normally their distance from the origin point would have been 1 over, 1 up, right? Or 1 over, 1 down. Their distances would have always been the same. 1 over and 1 vertical. All right, so what that's telling me now is that instead of going a distance between our origin point and our initial points, horizontally, that distance is only 1/2. And that is half of the parent distances. All right, it's half of the respective parent distances. You can go all the way along the whole formula and do, or function, and do the exact same thing. What's the difference between negative 25 halves and negative 3? Right? These two values up here. What's the difference between them? Well, negative 25 halves is negative 12.5. To negative 3 is going to be, what, 9.5? All right. Double that, we get our usual distance. Nope. Between negative 27 and negative 8, that's a distance of 19. All right, I screwed up there, but Whatever, it's fine. Oh no, 9.5, right? So double 9.5, you get 19. There we go. So this means by putting a 2 in this particular position, we have now halved all of our x distances from what they should have been in the parent function. Right? So what does that mean? Well, that means that this particular value, whatever it might be, is always going to shrink, or my preferred word of choice here, compress. Not x values, x distances to the origin point. All right, look at the x distances that go to the origin. All those x distances between those 2 points all the way down the list are just going to get halved, all of them. And again, you can look in terms of what that's, whether or not that's true. Okay, what about the 5 that's being multiplied on the outside? Okay, well, that took our -3 and bumped it to -15, -2 bumped it to -10. Right, this is going to be a stretch factor. Okay, so we have stretch factor of 5 in the vertical direction. So this is going to stretch or factor the y distances from the origin point. Right, so what's the difference between -17 and -12? It's a difference of 5. What was it originally? It was -3 and -2. 1. So we have quintupled all of these distances by having this 5 out front. All right, shouldn't be a surprise. It's just kind of the way things work there. So, what does it mean then? Well, it means we have a whole setup. We've got y equals a times some function of b times the quantity x minus c plus d, where we said a was going to be a vertical stretch factor. D is going to be a vertical shift, again in the same direction that we see whatever sign it is. All right, B is going to be a horizontal compression factor. Some people call this a horizontal stretch factor. I prefer it as a compression factor because now you don't have to think about what it does, right? You know that if I increase the value of B, it is going to compress it more. So I am letting my language do the heavy lifting on this one. All right, and C is going to be our horizontal stretch factor. No, shift, horizontal shift. Jeez. So when we've done this, again, this allows us to be able to come up with not only the values fairly quickly, but also then a graph of this particular thing, again, fairly quickly compared to like somebody who would sit down and painstakingly be like, what x values do I want to use over here? I just say, this is bullshit. We're going to start with the parent function, and then we're going to change all of our x values that we get for the parent function to wherever those, this is the other thing, wherever those particular parent function points got mapped to by these transformations. Let me be explicit about that. These are the same 7 points right here as these 7 points here. These 7 points that I graphed here are the same as these 7 points that we graphed here. The only difference is that they have been stretched and moved around until they fit in these new locations. This is a little bit weird, maybe, if you've never heard this before. But it's the transformation took these 7 points and turned them into those 7 points. X values here, Y values here. This is super important, right? If you could get that, you will be able to do graphing of function transformations in a fraction of the time as somebody who's like, you know, picking up their calculator and trying to decide like which x values do I want to show on a graph, because I don't know, it's going to be hard. Maybe I'll have to go out further and just make my scales bigger so that I can get integer values. Guess what? I don't care if it's integers. I don't even care what kind of numbers I get. But tell you what, right? The values we get off of the cube root function, off of the parent function, those were integers to begin with. We did this on purpose. We picked these values because they were nice. But I know students who would go through and be like, 1, 2, no, not 2, 3, no, not 3, 4, not 4, 5, 6, 7, 8. We'll use 8. Right? Don't go through it one step at a time and take forever. Right? You look at it, you be like, this is how I want to do this. I want to start with the values that give me nice things first, and then transform them out to wherever they're going to be. So, my preferred method, start with your parent function. What are your inputs? What are your outputs? And then how do those get altered every time you go and change your y values to be more like the transformed one we want? The y, right? And then over here, take our alleged input values to the parent function and say, okay, well, that was 2 times the quantity x minus 1. So solve, in other words, first divide by 2, get x minus 1, add 1 to just get x. Where are our x values? All right. What do you think? This can be done with any other kind of function. So I also did this with exponentials, I did it with logs, I did it with trig functions, I did it with some other stuff that we saw much later on in like calc. I was like, hey, you remember this stuff that we talked about in Precalc? You know, those of you, the 3 of you who had me for Precalc, how do we go back and look at this in terms of that function transformation stuff? Isn't this much easier now? Okay. Thank you everybody for the follows. We're going to raid out right now. We have Astro Canuck is doing some science, although I suppose he's doing a Lego Polaroid camera. Interesting. We got a lot of gamer type people. but I think we're going to stick with something educational. Dawn Does Math is doing the new Phasmo map, so if you are looking at all at... oh, you know what? We're going to go see a dinosaur dig. So, yeah, Danny is... Or no, not Danny. Dawn is checking out the new Phasmo map, so if anybody's interested there, Dawn Does Math. Tonight is Dawn Does Scary. We're going to go see Paleontologizing, who is Dr. Danny Anduza, and he is a paleontologist, digs up fossils. At the moment, they're at a dig site in Wyoming, near Green River, Wyoming. And so we are going to go check this out, because they have found a new... I'm not sure which... Was it Arcs? Oh, nope, Ceratopsian. They found a Ceratopsian. So this is a new horned dinosaur that they're not sure exactly what it is. They're going to kind of parse it out and figure it out. So, hope everybody has a good night and a good rest of your week. My name is Obi-Wan Pez. This is N Simplex Pachinko. We will be back here certainly next Tuesday for math, possibly also tomorrow, Wednesday. And then we'll also do some gaming stuff in between now and next Tuesday. So, hope you all have a good time, and we'll see you soon. This is Obi-Wan Pez for N Simplex Pachinko. Have a good night.